Aaron Nuba for the EE503 Project 5 assignment. To start, we have the definitions for the project. I make a call to code written by Dr. Kramer for the control modules. Next is section 1, where the duty cycle is fixed. Here's the equation to define the duty cycle. This selection is for the switches I'll get into when I pull up the Simulink. I make the simulation call, and then I make timestamps for the transient and steady states. I wasn't able to make one for that represented both transient and steady state for all the values, so I broke them up into individual ones. Next, I plotted all of them, and then I made calculations based on those plots, such as the IRMS, the ripple, the average voltage. I displayed all of those, and then did the same thing for the IRMS, and then down here the THD calculations. It's the same for section 2 and section 3. Really what changes is the duty cycle, but I don't have that code in MATLAB. So moving over to the Simulink, here's the Simulink model. To start, here's the duty cycle calculations. We have the constant D for part 1. We have V out nom and VC. These two, V out nom minus VC is the voltage error, which then feeds into both of the transfer functions, both Model 1 and Model 2. Model 1 is only this transfer function designed to regulate the swell of the voltage from this from the step block down here. And then we have these two switches controlled by these two variables. The reason why there are NOT gates here is to get the logic to work, because if I told switch gate to be 0, without this NOT gate it would be false and would be these two down here when I wanted it to be true and be D up here. So these NOT gates are to make the logic easier to understand for me. Next is this controller. What it does first is it's similar to this one, and then it reads the voltage in, and then it takes the voltage error, but it feeds that into a second controller along with the absolute value of the voltage. And what this is trying to do is it's trying to regulate the voltage through regulating the current, which increase power factor and get the current to follow that sinusoidal voltage graph, of which basically is sine of VAC absolute valued. So then we have this. Then this feeds into this controller here. Goes into this proportion controller. This goes into the switch, and then this goes into this switch, which goes into D. Down here we have the inductor. The inductor this is the input to the inductor, the voltage input. Due to the rectifier, this only sees positive voltage, which is why we have this absolute value block in here. This VIN is for before the absolute value, and then this is for after the absolute value. So this goes through here. This is the positive voltage across the inductor. It builds up positive voltage, wants to push stuff through the inductor. And then this is the negative voltage VC when the MOSFET is closed, indicated by B, which is just Q naught. This is when the MOSFET is closed, this is when the MOSFET is open and it's flowing through the path with the capacitor. So that's why this is subtracted, but it's only active when Q bar is active. This feeds into the inductor, this is divided by the inductance, and then this is the integrator. The integrator should be positive, which is why it's bounded. This gives the integrator current, which I also sent out. And then this is the capacitor. It's similar. This is the current flowing into the capacitor, but it only flows in when the MOSFET is open, Q naught. So the current from the inductor flows in, and then this is positive. Some of the current does flow out, and it flows out into the load, which is what this right here is. This is the voltage across the load divided by the resistance of the load to get the current flowing out, and then that is divided by the capacitance to get the integrator for the capacitor. This is for the input current. It's the voltage in, the sine of the voltage in times the inductance, and that's because That's because this absolute value here from the rectifier, this creates regular hills. It's the absolute value of sine, while this is just sine, and it's the actual current that's flowing in. It's the actual way the current is behaving. And then down here is the sawtooth generator. We have the sawtooth, and then we have the pulse width modulation control. We have this from tag for D, which is from up here. And then we have Q and Q bar, which I labeled as B. This concludes the presentation for the EE 503 project number 5 assignment. Thank you for your time.